Okay, so the problems that we're going to be looking at next involve this doubling time statement. So what this basically says is if you have one of these population growth equations, P of t equals P naught e to the kt, and we need to make sure that the k value is positive, so it really is a growth equation, then the doubling time of P is going to be doubling time. It's going to equal natural log of 2 over the growth rate, basically. So next example is going to deal with this. So we have, say, this computer virus. It says spread throughout the internet. Studies suggest the first few minutes it grew with a growth constant of k equals 0.81 or 0.0815 inverse seconds. So there's example 4. So we say computer virus. Spread with k equal to 0.0815. I guess we could say inverse seconds. And then we want to say what's the doubling time of the virus. So part A, we want to find doubling time. And then part B, we want to go through and say if the virus began in 4 computers, okay, how many were infected after 2 minutes? And then they want us to say, what about after 3 minutes? Okay, so find the doubling time. This should be pretty easy. We're just going to use the doubling time equation and say, all right, it's natural log of 2 divided by the k value. And that will tell me, let's put that in the calculator, and that'll tell me about what the doubling time is. And the units will be seconds on this. So we get about 8.505 seconds. So for part A, that means every, around every 8.5 seconds, the number of things infected doubles. So part B, they say, all right, the virus began in 4 computers. So if I'm building a population growth model on this, my initial population is 4. We have e to the, they told me the k value, 0.0815 t. And so they say, all right, how many are infected after 2 minutes and after 3 minutes? 2 minutes is 60 seconds, so for 2 minutes we'll put 60 seconds in for our time. 3 minutes would be 90 seconds. No, that's completely wrong. 2 minutes is 120 seconds. 3 minutes is 180 seconds. I don't know what I'm... Anyway, so 2 minutes, 120 seconds. We'll put 120 seconds in for the time, and that'll tell us the population or how many are infected. And then 3 minutes, we'll put 180 in for the time, and that'll tell us how many are infected. So we'll do 4e to the power of 0.0815. First time's 120. So at 2 minutes, looks like 70707 computers are infected at 2 minutes. And at 3 minutes, I'm rounding to, I guess, the nearest computer. So it was like 706.6 but we can't have 0.6 of a computer infected, so we'll just round it up and say that the full computer got infected. Whenever it's 3 minutes, we get 9400696. And we'll round that last one up to 7 because we have another partial decimal after it's 0.6. All right, so that'll be about how many are infected after each of those amounts are given. So let's move on. Okay, we get this thing for radioactive stuff we called half-life. So we'll say half-life. Half-life. This is the time it takes an amount of a radioactive substance to decay, where half is still radioactive. And the half-life equation is going to be basically the same as the doubling equation. It's natural log of 2 divided by the k. And this will tell us the half-life equation for a decay problem. If we have radioactive decay. So next example, we'll go through and cover it, and then we'll move on to a couple other problems. So we say for this example 5, we have radon, say 222, decays exponentially. With half-life they tell us half-life is 3.825 days. And we want to know how long will it take for 80% of the isotope to decay. Okay. So what we're going to do here is we're going to use the half-life equation, which I said was 3.825. That equals natural log of 2 over k. And we're going to use that half-life equation to figure our k value out. So I'll multiply the k on up and divide the 3.825 back down. And we'll get k equals natural log of 2 divided by 3.825. So that's my k value. So the amount still radioactive will equal the initial amount, e to the natural log of 2 over 3.825 times t. So I'm using this in my radioactive decay equation. I'm using this for the k value in there. This is actually, oops, I say that should actually be a negative value. Let's see. Because it's decay. So yeah, this should be a negative there. Since it's decay, we use the negative of the k value. So now that we have that, we say, all right, if you start with A naught, that's the initial amount, we want to know the time it takes for, if 80% is gone, then 20% is left. So we want to know 0.2 A naught over on this side. So we want, basically, if 80% decayed, then we want 20% of A naught. left. So we're trying to say we got 20% of the initial amount left radioactive. We're going to try to figure out the time it takes for that to happen. So we'll divide both sides by A naught. That'll cancel out on both sides. I'll get 0.2 equals e to the natural or negative natural log of 2 over 3.825 times a t. Take natural log of both sides. Natural log and exponential e cancel. We get natural log of 0.2 equals negative natural log of 2 over 3.825 times a t. We'll multiply 3.825 on up here. So we want it out of there. And we'll divide the negative natural log of 2 back across. Then we'll put this all in for our time. So we have 3.825 times natural log of 2, all that divided by natural log of 0.2, all that divided by negative natural log of 2. And that'll equal about 8.881 days. So that's how long it'll take to decay down to where 20% still radioactive. Okay, so the next little bit we're going to look at is going to be some stuff about compound interest. So let's see here. So we get these two formulas. Well, first of all, I'm going to write down a theorem for, this will be formulas for E and e to the x. So we get E is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power. And we get e to the x will equal limit n approaches infinity of 1 plus x over n, all that to the nth power. So these are two formulas you can use to represent e and e to the x. We're not going to use these too much here, but this is just kind of information that we'll say is good to know. Okay, so we have two different ways interest can be compounded. You can compound it n times per year, or you can compound it continuously. So we'll say kind of compound interest. So over here we have n times per year. And over here we have continuously. For n times per year, the equation is P of t equals P naught 1 plus r over m, all that to the m times t. And continuously is P of t equals P naught e to the RT. So these are our two equations. Oops. And I guess for this one we'll say P of t, this is the amount in account at time t. So this holds for both of them. T is time. R is the interest rate, but we have to write it as a decimal. P naught is the initial amount, which we call the principal. That's the initial amount or initial investment. And then over here, M, on this left-hand side, M is the number of times interest is compounded. Per year. So this one doesn't have M in it, but this one does. So the next problem is going to have us go through and just wants us to use these for a little bit, and then we're going to compare present value and future value stuff. Then the last thing we have is something called an income stream, and then we're done with section 5.8. So for this one, let's say, for an example involving those, let's say you invest $5,000 at 7%, compounded part A quarterly, part B continuously, for 8 years. We'll say how much is in the account do you have at the end of 8 years? Okay, so for part A, we're compounding quarterly, which is a n times per year compounding. You're compounding 4 times per year. So we would say the initial investment times 1 plus the interest rate is a decimal, divided by the 4 times you compound per year, all that times the 4 times you compound per year, multiplied by the 8 years you compound for. So its initial investment's 5,000, interest rate's 0.07, M, since it's quarterly, is 4, and T is the 8 years you invest for. Over here, so this will be our answer to part A, and for part B, if you compound continuously, it's $5,000, E to the interest rate, 0.07 times T, which is times the 8 years. So I'll put those both in, and since it's money, we'll round to 2 decimal places. So this one, we get $8,711.07 back from that. And this one, we get $8,753.36 back. So the slight difference is here you're compounding 4 times per year, and here you're compounding continuously, which means you're always compounding, which is compounding more times than 4 times. So the extra compounding leads to the extra money that you earned over here. So next up, we need to talk about present value versus future value. So we'll say the present value of P dollars received at time T is P e to the negative RT. So what this is going to say is if present value is like how much money do I have now, and future value will be if I invest that money, what does this present value amount of money, what does it grow to over that investment period? So kind of what happens is when you're trying to compare, like, is it better to get like $50 now, or is it better to get like $80, invested after 6 months at a 8% interest rate? Since the $80 that was invested at the 8%, that's in the future, you have to kind of bring it back to present value stuff, so you're comparing money in the same time period, because it might turn out that if you take the $50 now and invested it for the 6 months at that rate, that might lead to a larger number than 80 or something like that. So the next example we deal with is going to go through and use this to kind of compare a couple things. So this is example 8. And it wants to know, is it better to receive $2,000 today. Or $2,200 in 2 years. And they say consider an interest rate of 0.3 and then consider an interest rate of 0.7. Okay. So let's do the R equals 0.31 first. Okay, so you have $200 today. What we need is we need to find the present value of the $2,200. We need to find the present value of that for an interest rate of 0.3. So we get P e to the negative RT. So we get our $2,200. We get e to the negative, the interest rate is 0.03 times t, which is 2 years. So we'll put that in our calculator, because this isn't one you can really do in your head. And we get that this is about equal to $2,071.88. So you're comparing this, this is the present value. So you compare this to the $2,000 and you say, well, this is a bigger number in present value money. So in this case, it would be better to get $2,200 in 2 years if the interest rate is 0.03. So basically, you pull the future value of $2,200, you pull it back to present value money, you compare it to the present value $2,000 that you could get, and you see which one's bigger. Say, what if the interest rate is 0.07? So we get $2,200 e to the negative 0.07 times the 2 years, and that'll be about equal to $1,912.59. So that's the present value if the interest rate's 0.7. So you're comparing that versus $2,000 of present value money. So in this case, it would be better to take the $2,000 now, because you could take that $2,000, invest it at the 0.7, and after 2 years, you would end up with a value bigger than $2,200. So in this case, it's better to take $2,000 now if the R value is 0.07. And so basically why it worked out that way is the higher interest rate, you can invest less money and have it grow to a larger amount because of the higher interest rate. So that's why the present value, when the interest rate went up, the present value of 2,200 went down, is because a smaller amount of money will grow to a larger amount. Whereas here, when the interest rate was down here at 0.3, we could say that pulled back to a larger amount of money. So that's how you use present value to compare these. The last thing we need to talk about from this section is present value of an income stream. And we'll get that in the third part. That'll be our last thing to do.